The last talk of today will be given by Andreas Krause, who is professor at ETH, and he's going to talk to us about safe exploration in reinforcement learning.
So I'd like to start by thanking the organizers for putting together this fantastic conference at this point in time. I think it's super important to get the fields together, and I'm very thankful that they invited me. I'm super excited to be here today and to tell you about some work that we've been doing in the context of safety and risk and reinforcement learning, in particular in the context of exploration and system identification. And this is joint work with a fantastic set of PhD students and collaborators that I'll acknowledge as I go along. This will also connect to some of the concepts that Angela Schillig already talked about and touched upon in her talk earlier this morning. Okay, so we live in a world where an increasing number of decisions are made by systems that learn. And these systems learn online. Maybe the most ubiquitous example of this are recommender systems. Right? These systems that try to figure out what we like by observing how we interact with the content that they show us, right? Whether we read that article or buy that product or click that ad, etc. Right? And it means that the very decisions that these systems take becomes the very data that they're being trained on. Right? It means that we very quickly leave this nice, cozy setting of IAD supervised learning that we're also familiar with and really have to think and take seriously feedback loops and learning. Right? And I think this is really a call to action to bring these communities together to take these questions seriously. And of course, in the machine learning community, that subfield that maybe is most focused on this, the context of reinforcement learning, right? A model we've seen many times, where there's this agent situated in the environment which it can affect using actions to hopefully try to generate some reward and some good outcomes for it. And of course, these are precisely the settings studied in control, adaptive control, and so on, maybe with a little bit of different notation. So I hope you apologize for me sticking with the RL notation for now. We'll come back to some more control theoretic setups towards the end of this talk. Okay, okay, so let's see. Very good. And so, of course, one of the central challenges in reinforcement learning is this dilemma of trading exploration and exploitation, right? The agent doesn't know how the world works, so it needs to deliberate. How do I carry out actions to figure out how the world works, versus how do I use what I learned in order to make better decisions? And RL, of course, has been around for many years, as has been controls, but there's been quite some recent breakthroughs in reinforcement learning, fueled in particular through advances in deep learning, say in the context of Go and so on, right, that we all have seen mentioned. But I would argue that a lot of these breakthroughs really have been in situations where we have a perfect computational model of the world. Right? In Go, in particular, we know precisely how the board is going to look once we and our opponent have taken their moves. And this means that exploration is really a computational concern. And if you have computational power of Google and the like, then we can really simulate a lot of agents playing against each other and trying to learn about the consequences of their actions. But if you think about applying reinforcement learning in real-world applications, like autonomous driving, right, so medical decisions, to various other forms of automation, we typically don't have a perfect model of the world, and that means that trying out an action has potentially injurious consequences. And what we've been thinking about really is how should one actually think about notions such as safety and risk in the context of exploration. And I would argue as long as you actually start deploying these systems and really have them learn online, any action that they take is exploratory. So we really have to understand that question. Okay, so let's go back to this perception action loop, right? And of course, we have to first define what safety even is, and that's a difficult question. So one might be able to say certain states and state action combinations that I really would like to avoid, and maybe express those with a set of constraints. The problem is really that ahead of time, you don't know the dynamics of the world, right? That means you don't know ahead of time which actions are actually safe, or which actions will get you into states from which you can't recover. And that's really the fundamental problem, that you basically have to deal with constraints that you don't know ahead of time. Right? And that's fundamentally the problem we need to understand. I'd like to tell you about some thoughts we've been exploring in this context, and to that we need to go more formally in different settings. And in reinforcement learning, there's sort of these two broad kinds of approaches, right? Model-based RL, where we first try to elicit, identify, learn a model of the world, and then act accordingly. And of course, what's called the model-free setting, where we would say consider a family of controllers, of policies pi, and directly optimize over the long-term value of those policies as a global optimization problem. And so I'd like to start exploring and discussing some of these ideas in the context of model-free reinforcement learning, but I'd actually like to put the free in quotes, because we in the end will actually be using models for this long-term value. Okay, and so I'd like to ground these discussions in the context of a real-world application, and this is a collaboration that we have with the Paul Scherrer Institute. That's a large federal research facility in Switzerland who are in the process of finalizing the SwissFEL free electron laser. That's a 700-meter-long linear accelerometer, about 30 kilometers from Zuerich. And this instrument generates short X-ray pulses of extremely short durations, of femtosecond duration, 1/millionth of a billionth of a second. And using such an instrument, one can image extremely fast processes like molecules turning into each other in the context of chemical reactions. And that has lots of potential applications ranging from materials to drug design and many other areas. But it's also quite a complicated machine with lots of literally moving parts. So the way it roughly works is that there's an electron source. These electrons undergo sort of a sequence of magnets arranged in a snake-like fashion called undulators. And these basically shape the intense X-ray radiation that this machine provides. And of course, the question is about how to configure these magnets and move them around in order to shape the beam into the properties that they actually like, right? You like to maximize intensity, and you like to control the pulse frequency, pulse energy according to application requirements. But the system is also extremely sensitive with respect to environmental conditions like humidity, temperature, and so on. These constantly fluctuate, and one needs to adapt, and also needs to adapt according to different application environments. Okay, so this is quite a challenging problem, and in fact, there are safety constraints. You don't want to break that machine. How could that happen? Well, there could be beam losses in various different places, and these might demagnetize the magnets, and that you really don't want to happen. That's extremely expensive to replace. Okay, but fortunately, there's a range of beam loss monitors that sort of monitor whether you get close to doing something unsafe. So you might think about this sort of in the following kind of cartoon where we have this black box, right, our laser, and we'd like to input some control parameters, right, configuring these magnets in order to try to optimize some notion of reward, say the beam energy that we can produce. But at the same time, we don't want to incur these beam losses. We also have constraints, right, that quantify these beam losses. The trouble is we know neither F nor G ahead of time. Right? That means that the only way to learn about them is to actually carry out an experiment and, according to the measurements, decide how to proceed. Now, the goal, of course, is to maximize, say, the intensity, maybe cumulatively over time. We can talk about different aggregations while satisfying these constraints. And, of course, you'd like to do that every step along the way. So we not just eventually want to find a feasible solution, but one for every step. So basically, the problem you have to solve is try to optimize an unknown objective under unknown constraints while guaranteeing feasibility every step along the way. Okay, so I should have convinced you that this is a completely hopeless problem, at least in general. So you'd like to understand a little bit of when does this actually become tractable. Let's start with a little bit of a cartoon here in the simple setting where you just a one-dimensional f that's equal to the constraints. So we would like to optimize f while making sure that wherever we evaluate, we stay above this the safety threshold. Okay, now if you don't know anything, even the first action could be infeasible, right? So the first thing we'll assume is that we have a starting point, right? Maybe an initial controller derived from first principles physics models that we can start to explore from. Okay, but that's not enough, right? So if there is no structure whatsoever, there's no hope to generalize, right? So the second action could break us. Okay, so if we want to have any hope, we need to make some sort of assumptions, right, that we can exploit, some sort of regularity assumptions that we can try to extrapolate from and generalize from. Okay, and so one natural assumption might be some kind of smoothness, right? But then even if you have the smoothness assumption, we shouldn't really expect to be able to get to something like global optimum, but what you can really only hope to get to is sort of the best solution on the connected component of the feasible set that contains our starting point. Okay, and we'll call that the reachable optimum. It's going to be our benchmark. Okay? And so now, of course, we somehow need to express these assumptions about how these functions might look like. And one natural way to express prior assumptions is to take a Bayesian point of view. So we are going to endow the objective and the constraints with the Bayesian prior. And that's exactly what's done in the field of Bayesian optimization, where you basically put Bayesian priors on the objective and the constraint. And now these models, these surrogate models, allow to make predictions about the function where we don't have experiments, but we also can predict the uncertainty, right? Quantify the uncertainty in the prediction. And that predictive uncertainty can then be used in index-based policies in order to navigate this exploitation dilemma. And there's been a huge amount of work over the years exploring the setting both in the unconstrained setting, but also with constraints. But existing work in the context of constraints really sort of heuristically try to encourage feasible solutions eventually. But there's no, so in general, it will produce happily unfeasible solutions along the way, and there's also no guarantees associated with it. Okay, so now also at this point I would like to say, so this is sort of the place where we can really try to plug in assumptions, right? So, and I think in settings that involve physical systems and so on, we really want to make use of what we know, right? And Bayesian perspectives sort of give a very natural way of encoding prior assumptions. And there's a lot of nice works, for example, by Sebastian Trimpe and his group to think about what sort of the right Gaussian process priors you might want to use, say, for linear dynamical systems and so on. So there's lots of prior knowledge that can sort of infuse these models. Okay, so now how can you use those? So here's sort of a cartoon, right? Suppose we can get ourselves in this position where after carrying out a bunch of experiments, we are quite confident that the true objective lives somewhere within these gray confidence bounds. Okay, so we believe that with very high probability, the true function lives somewhere within these gray areas. Why is this useful? Well, we can sort of try to get a pessimistic estimate of the optimum, so the maximum lower bound, which is this green dashed line. And then, well, we should expect that the maximum should be somewhere within these green areas here, right, where the upper bound exceeds this best lower bound. And that's sort of the typical rationale that sort of justifies this optimism in the face of uncertainty principle, right? Picking the point that maximizes, say, the upper confidence bound, which is the widely used strategy in RL, bandits, Bayesian optimization, and the like. Okay? But we also want to think about safety, right? Maybe being too optimistic is also not the right thing to do. Okay, and so of course one can apply sort of the same picture and the same rationale for constraints, right? If this is now the model of our constraints and we want to make sure that we don't fall below the safety threshold, well, we can sort of try to construct a conservative under-approximation of this feasible region and try to restrict our exploration to this red set. Okay, now all this rationale is sort of nice, right? But it only works if you can actually construct these confidence bounds. And this is, of course, where the crux is, right? Now it turns out that, and of course, this depends on the model, right? And so we need to specialize. So far, I didn't say anything about what kind of model we use. Now, in context of Bayesian optimization, the most commonly used models are Gaussian process models. And those are non-parametric models that are very expressive, but they're still sort of tractable, so we understand them very well theoretically. Okay, now for Gaussians, well, you get credible intervals for one point, but just taking your mean and add some multiple times the standard deviation. But you really want to have sort of a bound that holds uniformly over the domain, right? If you want to apply this rationale from the previous slides, you want to be able to reason about this uniformly over the domain and uniformly over the steps of the algorithm. And moreover, maybe you shouldn't be too confident that you have really the prior distribution from which the true dynamics are being drawn. Okay, so it turns out it's actually possible to configure these confidence bounds to get frequentist coverage, to basically establish these confidence bounds even for adversarially chosen objectives, F and G, as long as they sort of agree with your prior. By that I mean that basically you need to scale these confidence bounds according to the reproducing kernel Hilbert space norm associated with the covariance function that this Gaussian process prior uses. That's this first term in this bound here that sort of quantifies the complexity, the agreement of the true function with your model. But then, of course, it also should depend on sort of how high capacity, how rich this model class is. If it's really, you want to accommodate a lot of different kinds of functions, you should expect to somehow admit a lot of uncertainty. And this is here this information capacity gamma, which somehow quantifies some kind of rate distortion. So how many bits you can extract about this non-parametric prior from a limited number of samples. And turns out this is actually so it's some sort of concave function. It is always sort of grows monotonically. And one can actually understand this analytically using ideas from submodular analysis. I'd be super happy to talk with you more about this offline. But this is actually a quantity that's very well understood. You can bound this analytically for different kinds of kernels. One can approximate it empirically using efficient algorithms and so on. So the main takeaway message is that we can actually understand sort of fairly well these credible intervals and confidence intervals that can derive for these Gaussian process priors, and that means one can sort of realize these pictures. And that suggests sort of one natural way of using them in exploration, namely, it's use standard algorithms, like, say, UCB, but always constrain the exploration with respect to the feasible domain. Turns out that actually fails, and I'll show you why in a moment. So instead, we do something different. So what we're going to do is we're going to build these models for both our objectives and our constraints. And we maintain a classification of the domain. So this red set here is our conservative inner approximation of the safe set. And among those points, we'll ever only sample these red points. But we are, among them, so going to pick relevant ones. What I mean by relevant, so one way for a point to be relevant could be because it's plausibly optimal, right? These points that I've shown in green before. But then look at this picture here, right? So now in this situation, the green set of points, these plausible maximizers, are contained in the strict interior of this red set. And at this point, the algorithm, if you just were to play UCB, right, or standard exploration strategies, there's no incentive to sort of explore the boundary. Right? That's why you also have to think about expansion, right? Trying to further identify and enlarge this feasible region. Okay? And that's what these purple points do. So these are called plausible expanders. These are points that plausibly allow you to infer that additional actions are safe. Okay? And if you now sample among them the most informative one, the most uncertain one, then it eventually actually finds the better solutions on this other side of the domain. That's sort of the cartoon of the algorithm. I'll spare you the pseudocode, the details on the paper, but one can basically prove under the same sort of regularity conditions that you need for these confidence bounds to hold that this algorithm is both safe and complete. Right? So you can basically establish for any given confidence level 1 minus delta, this is the probability of the noise realization that the algorithm will never make an unfeasible decision, and one can bound the number of steps it takes in order to find an epsilon optimal reachable point. Okay? And in general, right, we haven't made any assumptions, right? This is in general non-convex functions. So the sample complexity in general will be exponential in the dimension, right? There's no way to avoid this with the cause of dimensionality. But I'm going to talk about a little bit about that in just a moment. So here are some experiments that my student Felix carried out, actually in collaboration with Angela Zuerich, who is co-advising him. So these are experiments at Angela's lab, just to illustrate this algorithm. So that's certainly not as exciting as some of the videos that Angela showed earlier, but I think it illustrates the algorithm nicely. So it's basically this robot trying to solve the simple task of flying from A to B. It starts with some first principles controller that gets the job done, but it's not very efficient, sort of wobbles around. And so what Felix did is he injected different tuning parameters in this LQR controller and then optimizes over these tuning parameters, right, in order to get more aggressive behavior. And there's lots of parameter settings that would immediately destabilize the robot. So if you just do UCB, the robot would immediately crash against the wall, right? But by keeping track of the safety constraints, the robot actually fully autonomously experiments with its own control parameters without crashing. Okay, so it's just a little comparison. Good. Okay, so let me come back to the SwissFEL application that I mentioned before. So there's actually a lot of additional challenges that arise. So I mentioned these safety constraints, but here this is really a high-dimensional problem. You want to tune tens to hundreds of parameters. There's issues like heteroscedastic noise, so the noise depends on the input. You need to contextualize the different application requirements. One can simulate in principle, but simulation is actually extremely slow, extremely computationally intensive. So we really want to carry out experiments on the actual system. These are magnets that move around, so you can't just teleport from one parameter setting to the next, but you actually have to sort of plan a path. There's lots of interesting algorithmic challenges that arise that I'm very happy to talk more with you offline. But I just want to talk a little bit about this issue with how to scale to high-dimensional domains. And so the basic algorithm I've described before really requires basically this discretization. Obviously, that's not going to scale beyond the handful of dimensions. So one way to fix this is to basically sort of look at the sequence of problems that are simpler, each of which. Okay? And one sort of an extreme case is to basically just consider sort of a sequence of low-dimensional, in the extreme case, one-dimensional subspaces, and apply the algorithm only on sort of these one-dimensional subspaces. Right? So in the cartoon picture, you start maybe at this initial point here. You would pick, say, a direction, propose a direction, and then basically apply SafeOp to do line search, right, to find the next point. Okay, propose the next direction, keep going, and so on. Okay, and so it turns out that using this simple strategy, one can actually both get local and global rates. Okay, so global rates, one can basically converge at sort of Lipschitz rates that are exponential, but exponential only in the ambient or intrinsic dimension of the problem. So I'll say something about this in a slide. But also, in general, you can't really hope to get global convergence. But if you're sort of in the basis of attraction of a strongly convex local optimum, you converge there with polynomial dependence on the dimension. Right? So you basically combine sort of the benefits of local optimization and global optimization. And besides just random directions, there's also ways of proposing more informed directions based on this Bayesian model that we discussed in the paper. So here's just the picture that I had in mind, right? So basically, if it turns out that this function f of x really varies only on some low-dimensional subspace, so it's defined as g of a times x for some flat matrix A, then you only have exponential dependence on the dimension of this low-dimensional subspace. You don't need to know that dimensionality, and you don't need to know that subspace. And so we apply this on the actual device. So here's some experiments that my students carried out. And the algorithm does quite a bit better than sort of the standard local search techniques that are being applied there at the moment. Right? So you would basically take the existing parameter settings, detune them adversarially, and then sort of let the algorithm recover. And of course, by applying this sort of more global search, you can actually find better solutions. Right? And all of these actually produce feasible solutions along the way. So it doesn't violate any of the safety constraints. Okay, and so this now can scale to higher dimensions and so on. Okay, so there's other applications. I want to give a shout out to some exciting work at Caltech and Joel Burdick's group, and also in collaboration with Yanan Sui, who was one of the co-authors of the SafeOpt paper, and Yisong Yue, where they used the variant of the SafeOpt algorithm on a medical application for spinal cord therapy, and they actually used it in the context of clinical trials. So I very much encourage you to take a look at that work. We've also been using this in various other applications. One recent one is to use it in order to contextually tune parameter settings for building energy management and some other applications. So in the last 2 hours of this talk, I'd like to just talk a little bit about how some of these ideas can be used when actually modeling dynamics. Right? So far, this has been sort of very much this global optimization, model-free, quote-unquote, kind of setting. So I'd like to highlight how some of these ideas can also be applied when explicitly reasoning about dynamics. Okay, and so one very natural way to do that is to now basically, instead of modeling the value function, right, to directly model the dynamics. Right? So you can think about the nonlinear dynamical system that might consist of an a priori model along with an unknown disturbance, which is modeled with the GP, as has been done by a number of people here in this room, right? Really pioneering work by Claire Tauman, Amelie Zeileninger, Angela Jolik, and others, and so on. So this is a very, very natural model of basically combining deterministic information, first principles models about a system, with non-parametric capacity to describe deviations from it. Okay, and now why is this useful? Well, once you have this kind of model, you can sort of try to forecast the uncertainty using basically the uncertainty in that sort of model, and then try to come up with control strategies that avoid bad states under all plausible outcomes, right? And of course, the hope is while you keep doing that and keep collecting more and more information, one can condition, become less conservative, right, and basically explore larger parts of the space. That's sort of the high-level cartoon. And now, of course, the challenge is how to actually do this. Right? And so now one thing you can do is you can certainly use these confidence bounds that I've talked about basically for one-step ahead predictions. Right? If these confidence bounds for F, right, you can sort of predict one step ahead what are sort of plausible realizations of the dynamics. But of course, if you project multiple steps ahead, then sort of these sets gets very complicated. You have nonlinear dynamics. So what he showed in this paper at CDC last year is how to basically tightly over-approximate these Gaussian process forward dynamics using ellipsoids, which one can do very efficient polytope containment tests. Okay, and so given essentially these frequentist conference guarantees that I talked about before, these really give rigorous basically containment guarantees for all plausible dynamics going forward. Okay? Now, the problem, of course, is you not just care about one-step ahead predictions or five-step ahead predictions, but really safety is a long-term property. You want the robot to never crash, right? And so just reasoning that maybe you can go one step further, and one step further, and one step further, and one step further, well, now I actually can't go anywhere anymore, right? So this you don't want to happen. Okay, so now the question is sort of how can you avoid that happening? Well, you somehow have to think about sort of basically explicitly maintaining a subset of the state space that can actually be safe. And there's various ways of doing that using ideas from control theory, Lyapunov stability, and so on, that one can combine with these non-parametric confidence bounds that I've described before. So one way how to do that, we published in a paper at NeurIPS 2 years back, where now the safe seat, the safe starting point, is replaced by an initial stabilizing policy, maybe derived from a first principle model, linearizing the system, together with sort of initial estimate of a safe region in which this policy pi is guaranteed to keep the system. Now, what one can do is to basically sort of keep collecting information in that set, conditioning on it, which allows to certify a larger subset of the domain as safe. Right? And basically, one can continue exploration in that set. This policy pi will keep you in there, right? So I will guarantee to keep you safe. And basically, it will sort of keep expanding the subset of this region, which one can guarantee to remain in. Okay, and so under some conditions, one can even show that this allows to find, in a sense, a maximal approximation of the safe set. Okay, and now this one can combine with ideas from model predictive control, where basically one can now plan ahead both sort of a performance strategy using standard techniques from model-based RL, but also a fallback plan, right, a plan B, that will take you back to the safe set. And by tying them together at this first action, you know whatever happens in the first step, you'll be able to come back. Okay? And that one can do by basically using these ideas from reachability analysis with these nonlinear dynamics. Right? And this really works for non-parametric systems, right, modeled with GPs. Okay, so that's basically what I wanted to talk about. So the key sort of takeaway messages is one can actually get these non-parametric confidence bounds for rich models like GPs and combine them with ideas from robust optimization, stability verification, and so on, right? Really key insights from control in order to reason about sort of all plausible dynamics. Right? And then, of course, that raised the very natural question, how do I now go about collecting information to explore, right, to become sort of less conservative as I go along? There's lots of challenges going forward, right? How to go beyond GP models. We sort of heuristically apply these ideas for Bayesian deep learning models and so on. But of course, GPs are sort of what one can really understand analytically very well. How can one learn good priors if, for example, in the context of simulations? How do you scale to more complex domains? And of course, right, going beyond sort of static scenarios to really think about non-stationary environments, multi-agent interactions, and so on. So I also want to point out so that, that Felix and I recently gave a tutorial at the European workshop on RL with a lot more detail, and the slides are all online. Okay, with that, I'd like to thank all the collaborators of this work, and thank you all very much for listening.
Questions for Andreas? No? There's a question. Yeah. Go ahead.
Thank you for the great talk. So I think GPs are really good for Bayesian reasoning because you have tractable Bayesian analysis for them. But one of the challenges with GPs is that the conditions under which a function can be represented by a GP are very abstract conditions, like these Hilbert spaces and all these conditions. So for safety critical applications, do you have any intuition on when a function can be represented by a GP?
Sure. So I would argue that these conditions are actually not very abstract, right? So these RKHSs are pretty well understood. We know exactly how these functions look like, right? Maybe bounding them in general might be difficult, right? But they actually give a chance of really coming from sort of first principles limitations of coming from physics, for example, to really try to get a sense of what, say, the RKHS norm of function could be, right? Of course, in general, it's difficult, right? But at least there is sort of a handle, right? There's a hope to do this. Right, I think, right, so because one understands these spaces pretty well, it might actually be possible to do this. I think that's actually an advantage of these kinds of models.
Okay, questions? Yeah, there's one.
Hi. Here.
Yeah.
So for high dimensional embedding, that's also data driven, right? You have some initial data point and you embed into low dimension from high dimension. How do you track that uncertainty?
What do you mean? So in this line Bayesian optimization example?
Yeah.
Well, so exactly the same way, right? So I mean, if you look at the slice, right, of a GP on a subset, it's just a different index set, right? So still as GP, you can easily calculate what's the covariance function or the restriction and so on, right?
Okay.
So that's that one can.
So as you increase, as you add more data points, the embedding also becomes more.
So the embeddings remain one-dimensional, right? But you can share, because you have this joint model, you can share observations across different slices.
Thank you.
Yeah.
That's a question.
What sensors does your drone controller have?
So this was all externally observed, but the details Angela can probably talk more about, right? And certainly I can point you to Felix, who can tell you all the details of this experiment.
It's just the camera?
There's a camera system that tracks the drone externally, so this is not on board.
Other questions? I Can I ask a question myself?
Yeah.
So in the linear Bayesian optimization, when you do the random coordinate descent, how does the order or the choice affect either theoretically or empirically the outcome?
Sure. So, I mean, what we analyze theoretically is really literally random directions, isotropically with the Gaussian random prior, right? So, so in some sense, you sort of benefits from guarantees you get even for random search, right? But since you actually always compare with the current solutions, you also get these local convergence guarantees. So that's, but what we also discuss is how to use the model in order to propose more informed directions. Yeah. So for example, what you can do is once you so the derivatives of a GP are still a GP. So it means that you can sample, Thompson sample direction in which you can search. That's one technique that we used in the paper.
Okay, there's one more question.
Right here, sorry.
Yeah.
So your GP bounds are always in probability, right?
Yeah.
So, and it seems like a common case is that you're going to be active against a constraint. So, I mean, just you set up lots of optimization problems. The optimal that you find might be active against the constraint.
Yeah.
So doesn't that mean with some probability you're eventually going to expect, break your super expensive European instrument?
Well, so, okay, so the guarantees hold with respect to the noise realization, right? I mean, they rely on concentration bounds, right, from the noise, right? And now I think the point is more, so you might not want to, so become the strictly feasible. So we actually want to maybe guarantee strict feasibility, right? I think it's more a matter of where do you actually choose the constraint, right? But I think that's more the design of the feedback signal that you would get for the constraint function.
All right, it's 5:30. Let's all thank Andreas for a wonderful talk and a wonderful.